Welcome everyone to today's rendition of the point distribution webinar. Glad that so many people could make it despite the alternate time. Today we have speaking Paul Leopardi from the Australian National University, talking about diameter bounded equal measure partitions of Alfor's regular metric measure spaces.
G'day from Australia. I've got my slides up. You can't see my pretty face just yet. I'll probably switch that at some point. This is joint work with Giacomo Gigante of the University of Bergamo. And as per my usual, I'll go straight to the acknowledgements. This was work that was funded through the Italiazione Trail grants for visiting professor and scholar in 2015 at the University of Bergamo. And a lot of it was set up while I was visiting the Erwin Schrödinger International Institute for Mathematical Physics in 2014 on a program of minimal energy point sets, lattices and designs. During that visit, I did visit the University of Bergamo and a break between two of the workshops. I conducted this work while I was sessional staff at the University of Newcastle in 2015. And unusual acknowledgements, but my 2014 visit was actually funded through crowdfunding, and this is an obligatory page mentioning all of the possible supporters in 2014. Okay, so let's get going. I will mention the theorem now. Obviously, you'll need some definitions to put this into context, and I'll get to those in a second. We start with a connected Alfor's regular metric measure space of dimension d and finite measure, and then we can establish that there are positive constants such that for sufficiently large n, there's a partition of that space into n regions of equal measure contained in a large ball and containing a small ball. And those balls have the correct order of size, of radius that you would expect for that dimension. So here's the outline of the talk. I'll just briefly mention a motivating application, which is an application to numerical integration. I'm going to spend a lot of time, I think, in the talk just talking about the precedents to this result, which had to do with equal area partitions of the unit sphere, and that's the work that I'm most familiar with. Then I'll go on to talk about what makes this result possible, which is the dyadic cubes on Alfor's regular spaces, and then round up with just going through the construction at a high level. So the motivating result has to do with error bounds of positive weight quadrature rules on d-dimensional Riemannian manifold without boundary, and essentially the result here has to do with bounding the error of the quadrature rule with respect to a bound which is of the almost the correct order with respect to the dimension modulo this constant alpha, and the Sobolev norm with respect to that particular Sobolev class of functions. So that's one application. There are other applications which I'll mention in answers to questions later. Now, to get back into the dark past. The original construction and the original question being asked and answered goes back to Stolarski in the 1970s. Stolarski asserted the existence for any natural number of n of a partition of the unit sphere into n regions of equal area, volume, and diameter bounded as order n to the -1 on D. And I'm going to, by the way, murder every pronunciation of this whole thing. The one thing I should have mentioned is, while it is joint work, all of the brainy stuff is Giacomo Giganti, and all of the errors and mispronunciations and so forth are mine. Weiger and Steckman in 2002 gave a construction using a directed tree of Voronoi cells, and that can be modified to satisfy Stolarski's assertion. And that construction can be further modified to yield an equal measure partition of a compact connected Riemannian manifold. And I'm going to go into that in a little bit more detail. Firstly, reminding you about exactly what we mean by the unit sphere. We're calling it, this is just a set notation really, we're calling it SD, and that's in D plus 1. So, all the points of distance 1 from the origin in that particular real space. And just talk about what we mean by an equal area partition of SD. So it's a non-empty finite set of Lebesgue measurable subsets that partition the space in exactly the way that you would expect with the Lebesgue measure. Now, we have a notion of diameter of region. In the case of the sphere, because the sphere is defined by being embedded in Euclidean space, we can define the diameter of a region also in terms of Euclidean distance. So that's what we go ahead and do. So that's what we mean by the diameter is defined in terms of the super, the distance between 2 points in the region. Then we say that a set of partitions is diameter bounded with a particular diameter bound. Well, in this particular case, we're in SD, which is a d-dimensional manifold, and our diameter bound that we want is of order -1 over D, which is what you would want in terms of the way that the Lebesgue measure works and the Riemannian metric works. But in this case, we're actually using the Euclidean metric and the Riemannian metric as well. So this gives you a potted history. It goes in a little bit more detail of that history. Alexander in 1972 uses the existence of a diameter bounded set of equal area partitions on the 2-sphere to analyze the maximum sum of distances between points. And in that paper suggests a construction. That construction is actually different from a construction that was given by Zhao in 1995. The construction, I'm mentioning construction from 1995 because Saf and Sloan modified the construction, which was originally a construction for S2, they modified it for S3, and that then generalizes to the construction for SD, which I gave in my thesis in 2007. So that's one direction in which the partitioning worked. The other thing that you can do is follow the line of reasoning about the partitioning on SD. So as I said before, Stolarski asserted that the partitions on SD all existed in 1973, but didn't offer a proof. Then Beck and Chen in 1987 quotes Stolarski's result, and Bourgain and Lindenstrauss in 1988 quote Beck and Chen, so that they're sort of on air at that time in terms of actually having a concrete construction. But there was a paper by Wagner implying the existence of construction similar to the one in my thesis for SD, but not really spelling it out. There was also a paper in 1993 giving a partial construction. And then there's Fager and Steckman construction in 2002, asking a different question and answering it with their construction. It turns out that that their construction can be modified to a construction that proves Stolarski's assertion. And I go into detail on that in my PhD thesis in 2007. Just to give you a little bit more technical background, we're talking in this construction on the sphere about spherical caps. So the spherical cap is essentially a region which is defined by a circle, and that circle is of spherical radius theta. In other words, an angle to the center of the sphere of angle theta. And of course, what that means is that the inner product is bounded below by points within that spherical cap is bounded below by cosine of theta. So that's the inner product between any point on the cap and the center of the cap. And there's a well-known formula for the area of a spherical cap of spherical radius theta, which works for all D. So the construction, the modified construction where I modified for the Fager-Steckman algorithm goes as follows. First, you find a spherical radius of caps such that each of the caps gives you an area which is which divides the area of the sphere by n. Then you create an optimal packing of caps with spherical radius theta c. In fact, you don't need to create an optimal packing. You just need to create a packing which is saturated, and that's sufficient. You create a graph of kissing caps, which I'll go into some detail about below. You create a directed tree from the graph. You create a Voronoi tessellation. So there is, you partition the sphere into Voronoi cells, and then you start moving areas from the leaf of these cells towards the root of the tree, and then you split all of the cells that you get into regions which have the correct area. So it says here, create an optimal packing of caps. You don't really need optimal, as I said. The main thing that you have that you do require, though, is that you have a saturated packing, and the saturated packing is such that that there is no point remaining on the sphere such that you could place one more cap, and you must place the caps in such a way as they do not overlap. And that gives you a saturated packing, and the saturated packing is such that that if you take caps of twice the radius, then they cover the sphere. The next step is to create a graph, and all you do is you take the centers and you join them with an edge in the case where the spherical caps touch or kiss. You then take that graph, you get a spanning tree, and you make it a directed tree, which is directed from the leaves towards the root. There may actually be essentially two centers in the tree, and you could just pick one and call it the root. Next step is to create Voronoi cells around each of the centers. Once you've done that, then you start at the edges. Each of these Voronoi cells, of course, doesn't necessarily have an area which is an integer multiple of the area that you want to end up with. In general, though, they'll have an area which is more than the area of the sphere divided by n, which is what you need. And what you do is you start with the leaf nodes and move area in the direction of the tree upwards towards the, well, in the direction towards the root. And at each step, you'll be on a node which has more area than what you require for one region until you get to the point where you've moved the area into the root node. And at each point, at each step of that process, you're moving area from one node to a neighboring node and no further. So that's the way that the algorithm works. So there's a proof outline. So the packing radius is of the correct order. The Voronoi cells are in caps of spherical radius, which is twice that packing radius because of the either the saturation or the optimality of the packing that you had. Each Voronoi cell has area larger than the target area, as I said, and their areas are moved from the Voronoi cells of the kissing packing caps, which means that the adjusted cells are always in caps of spherical radius 4 times the original packing radius. So the diameter is bounded above by 8 times that radius, which is then a distance of the correct order. So I did run through that a bit quickly, but it does give you at least an idea of how the sphere is dealt with and how this particular algorithm uses the idea of a tree of, in this case, Voronoi cells, and moving area from one cell to a neighboring cell. So now that was like the appetizer. We'll now get to the main course. So by way of definitions, so firstly we have to deal with this idea, as mentioned in the theorem at the beginning, of an L4's regular metric measure space. So an L4's regular metric measure space at dimension D is a complete metric space X with a Borel measure, mu, with positive constants C1 and C2, such that all open metric balls, BXR, blah, 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 with R less than or equal to the diameter of X, satisfy bounds. Now, is that the diameter? Yeah, so anyway, there is a bound below and a bound above of the area of metric balls, which have a center within, well, anywhere within the space, and have a diameter anywhere up to the diameter of the space itself. So, in other words, C1 and C2 are universal bounds, and the bounds above and below of the Borel measure of the metric ball are what you would expect in a d-dimensional manifold. In other words, they're of order r to the d. So to cut to the chase, an Alford's regular metric measure space, excuse me, behaves like a d-dimensional manifold, at least to this extent. Of course, the space can be more or less wild, and the wildness of the space is tamed by these constants C1 and C2. There is a, if you want to go into more details, there's David and Sims, 1997, and Gromov in 2007. Now, we then take a look at this idea of dyadic cubes. There are two papers, one by David in 1988 and one by Christ in 1990. David basically comes up with the concept, and Christ then takes that concept and generalizes it. So a collection of open subsets of X, I won't read all of that, as a family of dyadic cubes, if there exists three constants, delta A0 and A1 with these properties. So the first one basically says that the measure of the union of all of the cubes that are at a particular K covers the space X to the extent that anything outside of those cubes has measure 0. The cubes do not overlap. Then the cubes have this idea of generations. So the idea of the generations is such that if you have a larger generation L, which is larger than the generation K, then either the cubes in generation L form two types. One which is, say, if you have a cube QK alpha in generation K, either a cube in generation L, QL beta, is contained in that cube QK alpha, or alternatively, it's disjoint. So in other words, you don't have cubes in a higher generation which partially overlap with cubes of a lower generation. Each cube is contained in a ball and contains a ball which is of the essentially the correct size that you would expect for that generation. In other words, order delta to the K. It turns out that these dyadic cubes are quite handy. But the main result is that these things exist in the first place. So David showed Alford's regular metric measure spaces contained in Euclidean spaces admit a dyadic cube decomposition. We then use the Swart embedding theorem to say that this decomposition holds for Alford's regular metric measure spaces. And Chris then gives a construction of the dyadic cube decomposition for a more general case. We only need the Alford's regular metric measure space for this theorem. And so the theorem that we're relying on is this theorem 8. Let X be an Alford's regular metric measure space of dimension D. Then there exists a family of dyadic cubes as in our definition. So that's the bedrock that we're starting with the construction. So essentially the construction has to do with the fact that instead you can't necessarily rely on this idea of a saturated packing of balls. in an L-force regular metric measure space, but you can rely on this, system of dyadic cubes. So essentially they stand in for this ball packing. So we start with the L-force, connected L-force regular metric measure space of dimension D with the constants C1 and C2. We then build our system of dyadic cubes. For sake of argument, because we start with a space which has finite measure, we can just assume that that measure is equal to 1. It just makes calculation easier. Now the construction, if you followed what I was talking about when I went through the construction on the sphere, should seem reasonably familiar. It goes along similar lines. Step one, well, what we want to do is partition our space X into n regions of measure 1 on n. So step one, we determine a generation of what we call large cubes. We create an adjacency graph. Then from that graph, we create a directed spanning tree. We do a couple of steps that determine a couple of numbers that we need. And in particular, this small m, which is our generation of small cubes. And then we do exactly what we did previously. In the case of the sphere, which is to move, in this case, measure from leaf nodes towards the root nodes, adjusting as we go, and splitting the nodes into regions as we go. So what we do is declare that we have n large enough such that we can, capital N, sorry, large enough that we can find a small n such that we have a generation of cubes such that the measure of each of the cubes is greater or equal to 2 on n. So, which is similar to what we wound up having with respect to the Voronoi cells in the sphere argument. Then what we do next is we create an adjacency graph, which is, excuse me, a connected graph with a vertex keeping track of each cube and an edge for each pair of center points, which satisfy this criteria, which is adjacency with respect to this constant A1, which is a constant which is governing the size of our balls, which have center those center points within each of the dyadic cubes, such that the balls have some non-zero area of overlap. So we're doing something to some extent similar to what we had with the kissing caps, but in this case we don't have kissing. We have overlap of metric balls with a radius which we're keeping control of. We use that to create a graph, gamma. We take a spanning tree of that graph. We mark one of the center vertices as the root and create a directed tree, T, by directing the edges and the leaves towards the root, which is, as I said, similar to what we did in the case of the sphere. We do a little bit of technicality here to determine this upper bound capital M, which is necessary for the proof to go through. Now, what we're talking about there is our cube beta and all of the adjacent cubes, Qn alpha. The adjacency there, we're talking about adjacency in the directed tree. So we've got alpha comma beta is in T. In other words, there's a directed edge from beta to well, there's a directed edge between alpha and beta. So we're talking about adjacent cubes which are adjacent in the tree. What this does is it puts an upper bound on the measure of a cube and its neighbors. And that's the technicality that we need for the proof to go through. The other thing we need is to determine a generation of cubes such that the measure of the balls that we're controlling in generation M is sufficiently small. And by sufficiently small, what we need is 1 on capital N, M times capital N. In other words, another technicality, but it makes the proof go through. It makes these small balls small enough. And that gives us our, settles our generation of small cubes. Once we've done that, we can then start with those cubes of generation N and then start essentially manipulating our measure, well, not manipulating the measure itself, but manipulating our regions such that, that we're sweeping measure from the leaf nodes up towards the root. And we do that in such a way as we wind up with an integer multiple of 1 on N worth of measure within each surviving region, well, each surviving node. So we wound up with a situation where, well, here in the leaf nodes, we have N beta cubes of generation M within our dyadic cube to be the nuclei of regions. And we then take that those nuclei and extend them into regions which have the correct measure. And we have a remainder, and with the remainder we sweep up into the nodes which are adjacent. In this particular case, because we started with the leaf nodes, they're non-leaf nodes. This is everything except the root. We have to deal with the root differently. So we split the non-leaf, non-root nodes into regions. Similarly, except the fact that we're dealing now with all of the measure that we've inherited from our neighboring nodes in the tree. But once we've inherited that amount of measure, we then do something similar. We wind up with a remainder of measure, and then we sweep that into, basically further in the direction of the root node. And what we wind up with is an amount of measure which is a multiple of 1 over n, and we then, have a splitting of that node using these nuclei, which are then extended to regions of measure 1 on n. And we deal with the root node differently, because what we have to do at the root node is to ensure that we have a multiple of 1 on n of remaining measure, including what was originally at the root node. But similarly, we have the cubes of generation m, and we then use those cubes of the small cubes as nuclei of regions which we then extend to 1 on n. So, I mean, essentially what we're doing is we have this system of cubes of 2 generations, the larger cubes being our containers with, representing each of the nodes that we have in our spanning tree. And we're sweeping measure from the leaves towards the root the same way as we did in the case of the sphere. But what's different here is the fact that we have our smaller cubes, which we're using as nuclei of regions. And because we have smaller cubes, that gives us the part of the result that says that we have each of the regions that we eventually get of measure 1 on n containing balls of a certain radius. Now I've whipped through this in probably a little bit too much speed, but that's all I've got in the way of slides. So for the moment, I'll stop sharing, and I'll here I am. Yes, so that's it, and thank you on behalf of Giacomo Gigante, and I'll now leave off to our host.
Thank you very much.
Yes, thank you for the talk. Really quickly, before we go to questions, because I forgot to say this at the beginning, as always, there will be time for just staying around and socializing if anybody wants to stay on after we go through questions. So, everybody's welcome to stay on afterwards. But yeah, so now we open the floor. Are there any questions for our speaker?
So thank you for the great talk. So I'd like to understand actually this last part better. So in the spherical case, right? So if you go back to the original construction,
yeah,
the way you transfer area between adjacent regions is you just slide the face parallel. Okay, and how do you do it in the in this non-smooth, in this alpha space case? We just
I think our paper actually skips on details there. It basically says that assumes that it can be done, but doesn't really go into any details about how one goes about doing it, other than the fact that you are in a metric space, and therefore some of the points that you have are closer to the node that you want to move measure to, and some are further away. So you would do the obvious thing, which is use the points which are closest. Now, as to whether or not that would violate any assumptions and make the whole theorem invalid is another question. So there may be some level of detail which needs to be filled in to take this to be being an absolutely watertight proof, but that's where we got to.
Yeah, so I guess the only issue would be to describe this boundary that you're moving or something like this, right? So as long as you have a boundary, you have seems like your measure is behaving nicely enough for this to be doable, just because of the alpha's condition.
Yeah, I mean, the other way that you could think about doing it is to the fact that you've got this system of data cubes. And while we have our second generation, which is smaller cubes, which support the smaller balls in the theorem, you could think of going to even lower, even higher generations in the system.
Right.
Move cubes from one region to another.
Yeah.
And just keep doing that, and basically you move
just
cubes of a sufficiently high generation, and you just keep going like that until you've got to at least approximately the amount of measure that you want to move, and you just basically just close it out by saying, well, you can go to as high a generation as you want. And really, it then comes down to whether you have to move something that you don't want to move. The thing is that the theorem does not say that each of the resulting regions are contiguous. They don't have to be, they just have to be bounded in diameter. I mean, one would think from the point of view of economy that they would be contiguous, but we're dealing with something which is not a manifold, and it may not be necessarily as simple as you think.
So something like not necessarily simply connected, or like very, very rough.
Yeah, I mean, it may, for example, work with graphs and a graph measure.
Okay. Yeah. So that's kind of hard. I guess I need to think about these rough domains. Another question is: so now suppose the domain is smooth, everything is nice, right? So so how long does it take to construct such a partition, right? So say you need n subdomains, right? And then it's what? It's O of, I mean, say you have how many calls to the manifold function you need to construct such a partition or something like this.
Oh God, we never went into that aspect of it. The computational complexity of the algorithm, simply because it's a theoretical construction based on the harmonic analysis of the situation, rather than something which we thought would be practically realizable. I mean, it'd be nice if it could be practically realizable in specific.
Oh, on sphere, it's very much practically realizable. You have these spiral points and so on, right? So.
Yeah, but I mean, the sphere's been done like to death. You want to be able to do something which can't be done by other means. But yes, coming back to that point about graphs, Scott, that we need something which is an alpha's regular metric measure space, a finite measure, which means that we need the right sort of measure for everything to go through. But yeah.
Yeah, obviously it doesn't make sense to talk about computational complexity if the set itself is if it's some sort of non-analytic crazy set. Yeah, then of course there is nothing, no computational complexity. It doesn't make sense.
Well, it does to a certain extent, but basically what you have to do is try and put some sort of bound on the generation of data cubes that you need to deal with. And, in our proof, there is no upper bound on the generation you have to deal with. All we say is that our small cubes, there is a generation of small cubes which exists that you can use, our small m. But we don't put any finite upper bound on that small m. So, and what you would wind up with is some sort of computational complexity based on at the first instance that small m, and then, as I said, the actual procedure of moving a measure from one region to another would then involve another generation of dyadic cubes, which would probably be much smaller.
Right. Yeah, I see.
I'm going to just say Carlos has had his hand up for a few minutes, so maybe we'll do his question next.
Hello?
Carlos?
Sorry, I'm looking at the chat and I can't see it in the chat.
No, it would be on his, it's on his screen, and it's also, if you were to look at participants, you could see it. But Carlos, can you hear us?
Hello, Carlos. I think he's having technical difficulties.
Probably. Can you write your question in the chat, Carlos?
It's probably furiously typing away on a mobile phone.
Okay.
Oh, I try, I see.
So you can hear us. That's good.
By the way, I'm not really the best person to answer a lot of these questions. Giacomo is, because he has much more extensive knowledge of harmonic analysis than I have, and I haven't really been looking at these questions for the last 5 years. So. Okay, he says, in my main theorem, also he says he doesn't know why his mic's not working.
Yeah.
It says for large enough n, I don't compute constants. Yes, that's true. In that sense, it's an asymptotic result, and of course, yes, you can actually say for all n because of greater technicality there. Once you've got that large enough n, you can always backfill. So that means that that you can actually say for all n in the theorem itself. In the construction, we use a large enough n, but once we've established that large enough n, you can use other techniques to deal with everything up until that n. Yes, okay, well, I'm not an expert on R4's regular spaces either. I'm a user of them, which is not quite the same as that. I mean, basically, I knew enough about the way that the dyadic cubes worked in this case to be able to follow what Giacomo was doing in the proof. And yes, there are some very strange examples that cannot be embedded in Rn. I'm not 100% sure, but that probably is the case. And yes, but I am sure that the proof is valid for the examples that can't be embedded in Rn, but simply because the proof doesn't require the embedding at all to go through. It just requires the existence of the dyadic cubes. So long as we're following the properties of the dyadic cubes and the properties of the measure metric space, we don't need to, well, the construction doesn't need to in any way reference an embedding. So we hope that the proof goes through simply because of that. Everything is done within the context of the properties that have been established. Yeah, well, nice to see you too, except that I don't think you got your camera on.
Other other questions for the speaker?
I did have an email from Giacomo, so I'll read out the bit which the main bit that pertains to this talk. He says, concerning equal measure partitions, let me say that I'm very proud of this result. It has been used widely recently by several authors, mainly the group from Austria and by Skriganov. He actually contacted me recently because he wanted to talk about our result in an advanced course he was teaching. Let me also mention a couple of recent results by myself with Garibaldi and Brandolini, where we use these partitions to prove the Koroval-Myers conjecture on the existence of optimal designs on Riemann manifolds and to prove a sharp version of Cassell's Montgomery inequality again on manifolds. Of course, your slides are absolutely good as they are. Only mentioning this in case somebody asks you about further applications of this result. So there are further applications, and that email came in a little bit late for me to modify the slides.
Actually, that's kind of funny because that was going to be along the lines of a question that I had, was that, right, so there are these results about spherical designs, about them being, well, about them being well separated once they're sufficiently large enough. And I was wondering if, these equal area, bounded diameter partitions happen to, somehow give you, where maybe if you put points in them, somehow they could give you points that were optimal in ways like either discrepancy or in the creation of designs, or or some kind of, or help you get uniformly distributed point sets.
That actually is a really good question. It doesn't pertain to this research quite so much as some of the other stuff, especially the research that I did with the group in Padova, especially, well, let me go back to the well-separated spherical designs. If you're talking about the paper that I think you're talking about, in that case, they do have an argument about splitting the sphere into regions, but in that particular case, I think they need the regions to be convex for their argument to go through. There's no, well, certainly in the case of this particular construction, there's no convexity. In the case of the other constructions, well, certainly the construction back on the sphere that I went through in this talk, there is no guarantee of convexity there either. You might be able to come up with some argument that says that you can do something there, but you're dealing with adjacent Voronoi cells, so you're probably not going to be able to do it as well as you might think. I did have a second construction in my thesis, which are approximately rectangular regions, but even in that case, they're not convex. They might be able to be modified to be convex. And I don't know what the state is of that theorem now, whether the convex regions are still required. Yeah, so I did do some recent work with Vianello and Somariva having to do with points on the sphere, but that was in a different context, really having to do with positivity of the weights, using the points on the sphere for positive weighted quadrature.
Okay, thank you.
So just to clarify about what you just said, so are there results which guarantee convex partitions on anything?
I'm not aware of them, but as I said before, I haven't really been active in research for a number of years. So I've sort of lost track of exactly what was happening in that case. I mean, obviously, if there is a result having to do with well-separated spherical designs, there must be an underlying result that says that the assumptions that are made in the theorem that proves that result are all valid.
I see. Thank you.
Any other questions? I will stop the recording now.
Okay, thank you.